All right, AP young people, trying to wrap this up. Hopefully it won't take me very long. So types of IMFs, types of intermolecular forces. These are forces between the molecules, remember. If ions are present, then you have ion dipole forces. If you have neutral molecules, that means you don't have ions present. Sorry about that. Then you have dipole forces, or London dispersion forces, or hydrogen bonding forces. So these are the four types of IMFs we could have in all kinds of different solutions, all kinds of different materials. Ion dipole requires you to have an ion. Dipole, London dispersion forces, and hydrogen bonding forces are for neutral molecules only. So these are all electrostatic forces in some way, shape, or form. They are all some sort of force that is created because of an electrostatic differential. The only one that is truly electrostatic, though, is the ion dipole. The other ones are pseudo-electrostatic, and I'll talk about that in just a minute. Okay, so an example of all of this, there are different bonds between people. You have the parent-child bond. You have an employee-boss bond. You have friends and friends. You have friends and lovers. You have lovers and lovers. And you interact differently with those people. There's a different interaction, a different sweetness, a different way you talk and you are with people. And that's kind of the same thing as the IMFs. Remember, these are between people. They're not what keeps people together. We're not talking about all the bonds holding a person together. We are talking about the bonds holding people together, relationships together. Okay, so similar kind of deal there. Okay, so ion dipole forces. Ion dipole forces exist between an ion and a partial charge. I'm getting rid of my face so you can see this whole thing. Okay, an ion and a partial charge on the end of a polar molecule. So remember how we said these are electrostatic? We have to talk about polarity in this. Because if it's not an ion, officially it doesn't have a charge. But polar molecules have a pseudocharge. That means they have one end that really likes electrons, and then they have another end that doesn't so much like electrons. And so what you end up having is this charge distribution that is not equal anymore because one really wants electrons and one really doesn't. And the one that really does will have a slightly negative charge, and the one that really doesn't will have a slightly positive charge. And so when we're talking about polarity, that's what we're talking about. So all molecules are either nonpolar, through polar, all the way to ionic. Ionic is the most polar we can get because that's when we have a definite charge differential. Okay? So when we have a polar molecule, that's known as a dipole. That means one side is positive, one side is negative. So we have an ion dipole. We're talking about ionic solutions in things like water, a polar substance. So a solution of sodium chloride or potassium chloride. Water is a really special molecule. So when we see a KCl dissolved into solution, what happens is the water has a positive end where the more electronegative oxygen is, a negative end where the more electronegative oxygen is, and a more positive end where the hydrogens are. So the positive K is more attracted or associated with the O, and the Cl, the negative Cl, is more attracted or associated with the H because of that. And so we get these little dotted lines that are the IMFs, the ion dipole forces that occur. We also call those IDF, okay? So this is a momentary kissage, it says. Basically, a momentary moment where they're like, ooh, okay, I'm attracted a little bit. Ooh, I'm attracted a little bit. It's not anything that's like, ooh, baby, I'm going to stay right here. It's a momentary, ooh, okay? So that's what you kind of get. KCl solution is used in IVs as lethal punishment for lethal injection. So KCl is not good for your heart because it causes the heart muscles to stop contracting. So this is what they would use in IVs to do capital punishment by lethal injection. Okay, dipole forces, or DDFs. Okay, This means we have neutral but polar molecules, and they're somewhat close together. So what does that mean? Both molecules have to be polar in order for this to happen. So we have one molecule that is polar and one molecule that is not. These are weaker than IDFs because IDFs involve a definite ion, and so there's more there going on. These don't have ions. These just have polarity. So as the dipole moment increases, so does the polarity, and so does the DDF. So as the dipole moment, which is signified by the Greek letter mu, or the polarity increases, so does the DDF. So the more polar a molecule, the more DDF it has, the more dipole-dipole forces it's going to exhibit. The less polar, the less dipole-dipole forces it's going to exist. Okay? So if you have a greater polarity, that means your dipole-dipole forces are going to be higher, therefore your boiling point and your melting point is going to be higher. So water has a higher boiling point or melting point because it has great dipole-dipole interactions. The oxygen and the hydrogen have a great difference in electronegativity, so we get that interaction. Okay? Phosphine is used in a pest control fumigation. It's due to high toxicity. It's a liquid phase. Phosphine is subject to DDFs because the phosphorus is the more electronegative and the hydrogen is not. And so the phosphorus has this kind of pseudo-negative charge, whereas the hydrogen is going to have a pseudo-positive charge. So we get a dipole moment where we have negative up here where the phosphine is, the phosphorus is, and we get positive down here where the hydrogens are existing. So that when phosphines are together, you will notice that their negatives and negatives are not next to each other. Their negatives and positives are next to each other, and that's how they interact with one another. So the higher those dipole moments, the greater the DDF, therefore the greater some of our physical properties. London dispersion forces. This exists between all molecules, but are the only forces between nonpolar molecules that are close together. So we get LDFs in everything. Everything is going to have an LDF, but we only say LDF if there's nothing else there. So if we've got two nonpolar molecules that are close together to one another, we have LDFs, and that's what we say. And basically what's happening there is we've got these electrons that are surrounding all of these things, and so they give them an instantaneous dipole every once in a while as that electron rolls around, which then causes the LDFs to go up. So if you have lots of substances with lots of electrons, lots of atoms with lots of electrons, you have increasing LDFs. So large nonpolar molecules are considered to have high LDFs. Okay? So like the gloop here. Okay? So large atoms with lots of electrons exhibit high polarizability. That means an ease with the charge distribution can be distorted a bit. So we can do different things with it. So just make sure you understand LDFs are nonpolar molecules, and it's because they have lots of electrons that are just kind of hanging out around stuff. And because of those lots of electrons, we can sometimes cause a momentary instantaneous dipole, which then gives you some interaction. LDFs are much smaller than DDFs, and they're much smaller than IDFs as well. Hydrogen bonding. Now, this is really funny because hydrogen bonding is a special class of dipole-dipole moment, okay? It's a special class of dipole. It is greater than a dipole. It has a greater interaction than a dipole. So it is one of the strongest IMFs that we can have. And hydrogen bonding exists between hydrogen and only 3 other things. It could be hydrogen and oxygen, hydrogen and nitrogen, hydrogen and fluorine. If it's not one of those 3 things, then it's not considered hydrogen bonding. Okay, they also consider chlorine here, but chlorine is a stretch a little bit because I've never heard of hydrogen bonding with chlorine, but I've heard it with fluorine, oxygen, and nitrogen. So anything that has a really great electronegativity. So anything with high electronegativity, hydrogen doesn't have high electronegativity. Fluorine is the highest, most electronegative. Oxygen is right after it. Nitrogen is right after that. Chlorine follows really closely to nitrogen. And so we get this situation if we have hydrogen in a molecule and fluorine, oxygen, nitrogen, or chlorine in a molecule, that we get this special class of dipole-dipole forcing that's called hydrogen bonding forces, or HBFs, okay? These are the most polar substances. You can see the polarity of these substances. So basically, hydrogen doesn't like electrons. It will donate all of its electrons and have this slightly positive charge. And all of these other things will take those electrons, will try to hold those electrons. So if you've got a hydrogen and you've got this other thing in this other molecule, they're basically coming together more strongly than any other of the DDFs would, the dipole-dipole forces. So actually, water doesn't have a DDF. Water has a specialized DDF, or dipole-dipole force, and that would be hydrogen bonding, okay? DNA has more hydrogen bonding than we can even imagine, and this is what keeps its structure so closely back together. Hydrogen bonding becomes extremely important in the replication of DNA and all of its processes. So you need to make sure that you're thinking about that. And other proteins too, hydrogen bonding is extremely important in those proteins as well. So hydrogen bonding acts between water and ice molecules. So we have water here, and water molecules just kind of come together and they just kind of float around in the solution, and they're all over the place, and they can get as close as they can get. But ice is a little different. Ice, because of its general nature, can only come together in one way. And you notice, instead of having these empty spots held together here that we can fill in spots because we're water, we have now these empty holes. And these empty holes actually trap air. They actually expand. Water expands when it freezes, which means that water as a solid has more volume than water as a liquid, simply because of hydrogen bonding. We can only get so close together and then be packed right because of HBFs, because of hydrogen bonding forces. And that means that the hydrogens of some of the water molecules are interacting with oxygens. And you will notice how very structured these are. Whereas up here, we can throw water anywhere it will fit as long as it doesn't interfere. There's still hydrogen bonding going on here. That's one of the reasons why water is so sticky. It sticks to stuff. It sticks to itself because of hydrogen bonding. But when ice is made, we get an expansion because it's as close as we can get right there. We can't get any closer without any movement and have these little holes there. So that is the end of the slide. Sorry I went so long.